nice to see you. So let us recall our discussion last time. Who will remind what is periodic motion according to our definition? So periodic motion, some repeating motion of an object which comes back to the same position after a fixed interval of times. So we consider mathematical model of so-called simple harmonic motion. What is the definition of simple harmonic motion? We mentioned it. What is required for a periodic motion which could be called a simple harmonic motion? Something was with acceleration. Acceleration should be proportional to displacement and aligned in opposite direction to the displacement. So when we have such conditions, and that is our well-known and studied already system spring block, we can claim that this is the simple harmonic oscillator, and this block is following a simple harmonic motion. So this is the most simple example for periodic motion. Any other periodic motions which could be more complicated, they can be represented in form of combination of different simple harmonic oscillators. So what we did last, we built a differential equation based on the expression for spring force and second law of motion, and we end up with so-called second order linear differential equation. We solved it and got the equation which describes position as a function of time, position of the block as a function of time, and that was some periodic. So we also considered two boundary conditions. So first boundary condition was at times t equals 0, we know the position of the block, so we consider that was in maximum displacement position A, x equal capital A. And second boundary condition that the velocity was equal to 0. So with this equation which we got for position as a function of time, we could take first and second derivatives over time, get expressions for periodic functions which describe velocity as a function of time and acceleration as a function of time. So we also introduced several parameters which are very important for simple harmonic motion, which is in any periodic motion, which is angular frequency, period of oscillation, and frequency. So now we continue our discussion of simple harmonic motion, and we will focus our attention on kinetic and potential energy as a function of time for simple harmonic oscillator. Also, we still consider this spring block system. After that, we will also introduce two classical examples of other systems which also follow this simple harmonic motion concept. So let us first recall here what we derived last time. We had position as a function of time, and that was A times cosinus omega t plus phi. Also, we need velocity as a function of time. So velocity as a function of time, v as a function of time is equal to minus omega times A times sinus omega t plus phi. So we have these two parameters, and now let us try to get expressions for kinetic and potential energy.
So kinetic energy of this system spring block, assuming that there is zero mass for spring and all mass is concentrated in the block and there is no friction, we can write that kinetic energy will be 1/2 mass of the block times v squared. So we have expression for v as a function of time. We need to substitute it here because we want to know kinetic energy as a function of time. So let me specify it here, kinetic energy as a function of time. So that will give us 1/2 times m times omega square times a square times sinus square omega t plus phi. So that's expression for kinetic energy. Let us write down also expression for potential energy. Who will remind me how we relate potential energy of this spring block system with displacement? Kx squared divided by 2. You're right. Good. So we write 1/2 k times x squared. So we know also expression for x as a function of time. So we substitute it here. Will be 1/2 k a squared, not cosinus, omega t plus phi. Okay, so now let us do some small transformation of previous equation for kinetic energy. We remember, yeah, oh yes, thank you, cosine square, sure. So we remember from previous discussion that in the process of solving this differential equation, we made a substitution, which eventually was our angular frequency. So there was omega is equal to square root of k divided by m. So we can see in this expression for uh, kinetic energy, here we have omega squared. So omega squared will be equal to k over m. Now let us substitute this k over m instead of omega squared for the kinetic energy versus time. This will be 1/2 times m times k over m instead of omega squared times a squared and times sinus square omega t plus phi. So here we can cancel out this m, and if we take a look on these three factors for potential and kinetic energy, three factors before periodic functions, they are the same. So we have 1/2 k a squared, and here we have also 1/2 k times a squared. So now our next step is to express the total mechanical energy of a simple harmonic oscillator. So this will be potential energy as a function of time. And this will be equal. So we can take out from parentheses this pre-factor, 1/2 times k a square. And in parentheses, we will have, probably let us first specify what it will be. So it will be kinetic energy as a function of time plus potential energy as a function of time. So this will be 1/2 k times a square, our parentheses, and here will be sinus square omega t plus phi plus cosinus square omega t plus phi. So this is the expression for total mechanical energy of a simple harmonic oscillator considered in the model system block spring. And now what can you tell about time dependence of this? So actually this total mechanical energy is a constant because this sum of cosine sinus square in of the same argument in the parentheses will give us unity. So we kind of automatically get rid of any time dependence. So here this will be unity, and we get total mechanical energy, already not a function of time because it's a constant, equal to 1/2 k times a square. And we can even specify that it will be constant. So what we see already here, that no matter at which time we consider total mechanical energy, it will be constant parameter and will be defined by the maximum potential energy of the system. So if you take a look here, for instance, potential energy of the system, here is 1/2 k times a square times cosine, some periodic function. So maximum value of this potential energy will be when cosine will reach its maximum value of unity, means that total mechanical energy is equal to maximum potential energy of the system. So defined by the properties of the string, its string coefficient and amplitude, maximum displacement of the block from its equilibrium position. This could be quite useful because sometimes we need to know what will be velocity of the block at any position, means at any also moment of time. So if we consider string block system which moves left and right, obviously string force will also go in different directions, depends what is displacement, positive or negative, of this block with mass m. And also it will be proportional to displacement. So if we want to know velocity of this block at any moment of time which corresponds to specific position x, and we apply this kinematic equation which relates initial position, velocity, acceleration, that will be quite a challenging task to do because this string force which is exerted on the block will be a function of position, means a function of time. All these factors should be taken into account. This will be quite challenging. However, with the help of this knowledge about total mechanical energy, that it remains constant for a system block string when we don't consider any friction force, we can simplify this task quite a lot. So what we can write: kinetic energy mv square plus potential energy 1/2 kx square for any position x. And that will be equal to some constant value, because no matter at which moment of time we consider sum of kinetic and potential energy, that will be constant. So it will be 1/2 k times a square. So from here we cancel out this 2, and we can write that v square is equal to k over m times a square minus x squared. Or eventually velocity at any position x which is of our interest, will be equal to square root of k over m. Here we can put plus minus because we may have either positive or negative velocity, depends on the displacement. A square minus x square. And also, if we recall that omega is equal to square root of k over m, we can write that this will be equal to plus minus omega, angular frequency of the oscillator, and times square root of a square minus x square. So that's a simple expression which we can obtain thanks to the fact of constant mechanical energy of such simple harmonic oscillator in order to get unknown velocity at any position of the block along axis x. So we can also take a closer look to this equation. For instance, if we consider position x, some extreme position, which is amplitude value, amplitude displacement, we see that velocity is equal to 0. So which correlates with our statement for block spring system when we claim that at this extreme position, when x is equal to a, potential energy is maximum, but kinetic energy is equal to 0. Yes, we indeed see that velocity is equal to 0. So now with this, let us move forward and introduce two systems which are classical examples of simple harmonic oscillators besides already considered spring block and a system. And I'm sure you already have an idea that it will be some pendulum. Yeah, you have a question? Sure. So this will be a pendulum. There are two types of pendulums in general which we are going to describe here. So first is mathematical pendulum, which has to satisfy certain requirements in terms of its shape. So it is some rod with attached heavy object to the rod, which can oscillate with respect to some equilibrium position. So there are certain conditions. First of all, the length of the rope should be much larger than the size of the heavy object attached to it, to its edge. Another factor, this rope should be not stretchable, so its length should be always constant. And its mass should be negligible in comparison to this heavy object attached, small heavy object attached to the edge of the rope. So in this case, we have maximum approximation to this ideal mathematical pendulum, and we can consider it quantitative. So let us do it and get some parameters of it. So schematically represent a mathematical pendulum. So here is some heavy object attached to a rope with length L. Here is some vertical line. So this pendulum is deviated with respect to this vertical line by angle theta. And we will have some forces exerted on this body. Here will be weight of the object. We also have some tension in the rope, which will be compensated by a component of this weight Here is angle theta. Here we have mg times cosinus theta. And also we will have some tangential component of this weight will be mg times sinus theta. So we can show here the trajectory, this kind of circular trajectory of this body attached to the rope. And as you see here, we deal with the driving force, which kind of moves this pendulum, is this component of the weight of the block. So it will be mg times sinus theta. So this is the driving force, which keeps this oscillation of a mathematical pendulum. And according to second law of motion, this tangential force, which is mg times sinus theta, it should be equal to mass times tangential acceleration. Mass times tangential acceleration. So in this case, we can write the following. So it will be minus mg sinus theta. So minus we have because this force, this component of the weight, will always try to reduce this angle theta. So no matter where this pendulum is located, this force will always try to put the pendulum into equilibrium condition when theta is equal to 0. Then we have it equal to mass times second derivative of displacement, which we mark as S. So when theta is quite small, the orientation of displacement vector and this tangential force will be the same. So let us recall how we deal with length of the segment of a circle. So this segment, it's the length of this segment, and when we have some angle theta, and here is radius. So length of the segment will be equal to radius times theta in radius. So here we deal with length of the pendulum. So ds, like small displacement of the block attached to the rope, will be equal to L, length of the pendulum, times d theta, like small change of the angle. So in this case, we can write that tangential acceleration, which is d square s over dt square, will be equal to capital L times d square theta over dt square. Taking this into account, we write that minus mg times sinus theta, the driving force for this pendulum, will be equal to m times L times d squared theta over dt squared. And m we cancel out. We can rearrange it a little bit. So we will get d squared theta over dt squared plus g over L times sinus theta, and that is equal to 0. Let's see. Yes. So this is our new differential equation, which describes, gives us information about theta as a function of time. So it actually describes how this block attached to the rope together as a system will move around equilibrium condition. So theta as a function of time. That's what we want to know. So if you take a look at this differential equation, it's kind of similar bit to what we had previously for our derivation of x displacement as a function of time for spring block system. So we had something like this. Let's move it. So it was d square x over dt square plus there we had k over m times x, and that was equal to 0. So you see these guys are similar, but there is a d. So obviously equivalent of x here is theta. So we have second derivative of angle theta over time plus here we have function itself, but here we have sinus of this function which we want to know. And that means that this is already second order nonlinear differential equation, which requires a lot of efforts to be solved. However, we can simplify this case and consider some specific condition when theta is quite small, so it's smaller or equal to 10 degrees, or something like 0.2 radians. So when theta is small, we can write with first approximation that sinus theta is close to just theta. And now if we substitute sinus theta with theta, we get d square theta over dt square plus g over L and times theta, and that is equal to 0. So in this case, we simplified second order nonlinear to second order linear differential equation, and we can solve it in the same manner as we did it for the previous equation for displacement of the block with attached to the string. So we will not do this step by step here because you can revisit our previous lecture in order to see how we solve this equation. But the solution will be exactly the same. So we can represent now theta as a function of time is equal to theta maximum, means amplitude deviation from equilibrium condition for this pendulum. And here we continue with cosinus omega t plus phi. And in analogy to previous case, you remember we had this substitution that omega was equal to square root of k over m. So in our case, we have g over L. So now here, omega is equal to square root of g over L. So that already provides us with information about angular frequency of mathematical pendulum. And we also can represent such parameters as period and frequency of mathematical pendulum. So period t is equal to 2 pi divided by omega, that is equal to 2 pi square root of L, length of the pendulum, divided by g. And frequency f is equal to 2 pi divided by omega. No, opposite. Omega divided by 2 pi, and that will be 1 over 2 pi times square root of g over L. So here are key parameters which describe periodic motion of this of mathematical pendulum: angular frequency, period, and frequency. And we see, for instance, for the period, if we pick up this parameter, we see that only length of the pendulum and acceleration of free fall, which at some approximation can be considered as a constant parameter on surface of the Earth. These only two parameters define the period of a mathematical pendulum, which is really important to highlight here that mass is not included. So no matter which mass you attach to this rho, if it satisfies certain conditions, first of all, mass should be much larger than mass of the rho, and second, the deviation from initial position of equilibrium should be smaller than 10 degrees, this angle theta, then period is a constant, so it does not depend on the amplitude. Amplitude can change over time, it can reduce because of attenuation of the oscillations of this mathematical pendulum. However, the period will remain constant because here we don't have amplitude value. So it will remain constant over time, which is a nice feature to use such pendulum as a measure for time. So first, reliable clocks were developed based on pendulums, and you looking at this equation, you can also guess another possible application of mathematical pendulum. Any suggestions? So what you can measure here? You can measure period. So the way how you measure period of oscillation, you measure some many oscillations, like 20, for instance, and measure time. So you divide this time interval by number of oscillations and get the period of one oscillation with this fixed period of time when the object comes back to its given position. And also we can measure precisely length of the pen. So there are two parameters which we can measure, and there is one unknown, which is acceleration of free falling. So that is a good system to directly measure acceleration of free falling, which is considered to be constant, but first of all, we know that it changes with height, so at different height it will be different. Plus, depending on the core, like Earth's core structure and composition, it may vary from one location to another. So that's another factor to be considered. So mathematical pendulum can be a simple and reliable device to do these measurements. You can, if you can design something similar to mathematical pendulum, you can even apply this equation and try to double check if indeed acceleration of free fall is something close to 9.8. If you get order of magnitude different value, then most likely your pendulum is not very mathematical. So now let us also consider another option which does not require any specific shape of the pendulum, because it may be any arbitrary shaped body which can rotate about some axis, let's say axis O, which goes through this. Obviously, this body should have some center of mass, which is located at some distance d from the axis O. So now, if we disturb such system, it will also, this body will also start to oscillate. However, it's not so straightforward as mathematical pendulum. So let us figure out how we can describe it. So here we can consider that the mass, like weight of this body, is exerted to the center of mass. So here is mg. And now we need to determine what will be the torque which exerted on this body with respect to axis O. So any suggestions? Let's assume that we know this angle theta. So what is torque? It's product of force to lever arm. What will be lever arm here? It's this distance. And this will be d times sinus theta. Sinus theta. So torque, the magnitude of torque, will be equal to weight, which is mg, times d sinus theta. We also remember from the topic rotation of rigid bodies that net torque, which is exerted on an object, rigid object, with respect to some axis of rotation, will be equal to the product of its moment of inertia with respect to this axis of rotation and angular acceleration alpha. Alpha is d square theta over dt square. So now we can write that minus mg times d sinus theta, again minus stands because this torque exerted on the body with respect to axis O here will always tend to reduce this angle theta and keep it in equilibrium condition when center of mass will be located on the same vertical line with the axis of rotation. Should be equal to I times d squared theta over dt squared. So we can rearrange it and we will get d squared theta over dt squared plus mg times d over I times sinus theta, and that is equal to 0. So again, we have this sinus theta. We want to get rid of it. We consider that theta is smaller or equal to 10 degrees. Then sinus theta in first approximation can be replaced with theta. And we get the simplified differential equation, which is just linear second order differential equation. mgd over I times theta is equal to 0. Again, if we solve it, the solution will be exactly the same as for previous two cases. The difference will be only in this prefactor next to theta, which gives us the omega square. That is mg times d over I, which is moment of inertia, or to be consistent, we can write that omega is mg times d over moment of inertia I. And obviously, theta as a function of time will be theta maximum times cosinus omega t plus phi. And in this case, omega is this omega, defined as square root of mass times g times d over I. So here we see that angular frequency already is a function of the physical pendulum. And here we need to take into account also distance from the axis of rotation about which this oscillation is happening.
and center of mass for this physical pendulum. And also we have this I in the denominator, which is the moment of inertia with respect to the axis of rotation, which we defined previously, like axis of rotation, about which this oscillation is happening. So if we know moment of inertia of this arbitrary shaped body with respect to its center of mass, and this axis goes parallel to axis of rotation. So we can easily apply this parallel axis theorem, which we considered previously, in order to get unknown moment of inertia. So that will simplify our life quite a lot. So now let us summarize our discussion. So we continue to consider simple harmonic oscillator, which is block attached to a string. We introduce concept of kinetic and potential energy as functions of time, which are also periodic functions by itself, but the total mechanical energy of the simple harmonic oscillator, we have shown that in this case it is equal to some constant, and this constant is the maximum potential energy of the system block spring, which is equal to 1/2 k times a squared. So taking this into account, we can determine velocity of the block at any position without necessity of going into these kinematic equations and considering time and position dependent force, like spring force, which accelerates, drives this block. So we also introduced the mathematical and physical pendulum as model systems for like classical systems for simple harmonic oscillators. We derived equations for the period angular frequency of this pendulum. We have shown that the period of mathematical pendulum does not depend on the mass of this block attached to the rope and defined only by length of the pendulum, and obviously by acceleration of free falling, which actually can be easily measured when we deal with mathematical pendulum. However, when we have a more complicated system, when we don't put these restrictions on the shape and can deal with any arbitrary shaped body, it can also oscillate because of gravitational force exerted on it. However, then we need to deal with the moment of inertia of this body with respect to the axis of rotation, mass of the body, like total mass of the body, and we need to know the distance between the center of the mass to the axis of rotation. So that will give us an option to calculate angular frequency of physical pendulum. We will continue this discussion of oscillations next time on Friday. And there we will introduce such parameter as friction or drag force, which will attenuate this oscillation. So amplitude will change over time. So we want to know how it's possible to describe this more realistic type of oscillation, because you know that if you provide some disturbance to a harmonic oscillator over time, it will decay its amplitude and its oscillation will be attenuated because of dissipation of energy via transformation kinetic energy into internal energy. So that will be our topic for Friday. Thank you very much for attention and see you next time.